Hello, this is Mark Unkefer. I'm Director of the Fiber-optic Sensing Association, and welcome to our February webinar. We're featuring a particularly interesting, exciting technology, a really opportunistic use of fiber-optic sensing, taking advantage of the network of fiber-optic cable that is available. In this case, it's to do opportunistic earthquake and ambient noise monitoring using DAS, again, on existing infrastructure. We're having as our presenter Dr. Martin Karrenbach, who is a Senior Manager of Innovation at OptaSense and has been the developer of this technology. He has a strong background in the area, Ph.D. in Geophysics from Stanford University, and is based in California. So, Martin, you have more than a passing interest in the use of this technology. We look forward to hearing your presentation.
Yes, thank you very much, Mark, for the kind introduction. And yes, California is primed to have earthquakes and other natural effects here quite frequently. And in this presentation, I'm going to show some concepts and learnings that we had on infrastructure fiber, where we interrogated with DAS systems. Infrastructure telecom fiber cables are all around us. We might not see it, but it's quite pervasive. And the primary use is for telecom data transfers, but they can be also, as we see, used very effectively for distributed acoustic sensing, strain sensing. And it has a multitude of uses, but we are limiting ourselves as to two in this presentation, which is some of the earthquake recordings and some of the ambient noise monitoring that you can do with DAS on infrastructure fiber. And those two are particularly important if you want to talk about earthquake alert systems. So that's why we picked those two. But before we go on into the actual presentation, I'd like to acknowledge the many collaborators and contributors over the last year or two to make these kind of analyses happen. All the OptaSense teams for acquisition and analysis, the various teams at Stanford, for example, where we show various data recorded on the Stanford campus. Also the British Geological Survey, where we show some of the recordings along train tracks, pick up some earthquakes on the fly as well. And also Caltech, that has been recording in Pasadena, in an urban environment, and also in the desert, together with the Jet Propulsion Lab that kindly contributed some of their expertise and investigations. On the industrial side, ENGIE and Telecom, we are very grateful for them to let us show the data that have been collected on one of their industrial pipelines in Mexico that captured some of the earthquakes that happened in 2017. And Starman Design and the Victoria and Albert Museum for some very novel and interactive visualizations of this kind of data. My presentation has a couple of key points, and I would like to start with describing very briefly what the DAS sensing system is doing on the fiber and how it is applied to infrastructure fiber. There's a difference between distributed sensors and point sensors. With point sensors, we mean seismic sensors or seismic broadband stations that are traditionally used for geophysical imaging or for earthquake analysis. And they do differ from the distributed fiber sensors that we use, but can be turned into one or the other, depending on the use. There are some key points for the infrastructure installation itself that have mainly to do with how a fiber cable couples to the ground and how it's able to pick up strain from the surrounding rock or soil and transfer it onto the fiber itself for measurement. Then we go on to talk a little bit about ambient noise and how to turn that ambient noise into an actual useful signal. That gives us a way to estimate the soil conditions, the near subsurface, and helps us then also to predict some of the ground shaking that might occur during a large earthquake, and then jump into the earthquake monitoring itself, and then discuss some of the opportunities that might be possible with infrastructure fibers in the next 5, 10, 20 years. So the motivation to use dark telecom fiber for sensing has a multitude of points. But I think the main driver could be that the cost per sensor is very low. So normally you have an interrogator system that sends out the laser pulses that is connected to a fiber. The sensing length can be tens of kilometers, 40, 50 kilometers long, and you can have 4,000 sensors in that little 40 kilometer section. So the sensor density along the fiber is actually very high. And most of the expense is in the box, in how you run the system, the optics, the electronics, and the recording of that data. And that's in contrast to the traditional sensors where you have just sparse sensors along a certain distance, but those sensors typically might record on their own, they might be powered on their own, and that drives up the cost of some of those point sensors, especially in the earthquake broadband seismic recording stations that are of high quality and need to be basically redundant and always on. So having a large sensor density drives down the cost. But in practical terms, if you look at the placement and the length, you can deploy fiber where you otherwise might not get to with standard recording systems or standard sensors, because at the time, then there might be roads, buildings, other structures that are prohibiting you from placing a sensor point there. And you can reach quite long distances. By daisy chaining some of those systems together, you can end up with thousands of kilometers of sensing length that is acting all in unison. Also, power is only needed for the DAS interrogator. So the DAS sensing system, that's the brains, and that needs to be powered. All the rest is just passive light transmission and reflection and scattering back into the box. The sensor cable is reliable over decades. It's very important that it is always there. It's unlikely to be stolen or vandalized. So if you think about deploying standard seismic systems in Southern California, for example, where our office is, you have a very high density of buildings, roads, an urban environment, and it's very hard to lay out any large amount of seismic sensors. People have tried, and those efforts are far in between because the chances of losing that system through vandalism and theft is quite high, and you might not be able to get to certain points at all. So having a fiber there permanently placed opens up a whole new world for you to sense strain in the subsurface and elastic and earthquake waves. So in some conditions, the fiber is in a very harsh environment, and it has been engineered to survive that. So high temperature, high pressures, low temperature, very anomalous environments, the fiber can still sense practically the entire strain field. But the last point I'm making down here is that the system can be always on. So it runs 24/7, continuously records data, and can generate real-time alerts based on the sensing measurements. But also, if you don't want to run the system 24 hours a day, every minute or every second, you can do some on-demand processing, or even just bring out an interrogator box, hook up to the fiber, and you have the system live for the entire length with those thousands and 10,000s of sensors. But let's look at where those infrastructure installations actually exist. And this is just a quick view of the worldwide installation that we have at OptaSense. This is one of the more recent snapshots. And you can see that we have tens and hundreds to thousands of kilometers of infrastructure fiber instrumented with distributed acoustic sensing interrogators. For various purposes, though, many of them are in the oil and gas realm, where you're looking at pipeline monitoring for leaks, security, or other purposes. Transport is another realm where you're looking at train traffic along tracks or roads, highways, or other transportations. Defense and security also use infrastructure fiber to defend certain assets against intrusions. And then just telecom applications where you want to ensure that the telecom facilities is secure. So just for us, we have about 25,000 kilometers in total shown here. And that is just the tip of the iceberg, because there is a lot of infrastructure fiber in the ground that you could potentially use for all kinds of purposes. But before we go into some of the examples, the key ingredients are really a fiber optic cable plus an interrogator. So the fiber optic cable can be a standard commercial off-the-shelf cable. And with the current generation of interrogators, you are seeing up to 40, 50 kilometers out from the interrogator to the furthest reach of the cable. So these telecom cables can be of various makes, models, and detailed constructions, but you always have a set of fiber bundles in there, sometimes as little as 2, 4, 6, sometimes on the thousands. And very likely, some of those fibers are not used. So while the majority is used for data transmissions for the primary purpose, you can use the dark fiber that is available to hook up some interrogator and use it for sensing purposes. Although those cables are not designed for sensing per se, they can still be used. And we go into that a little bit later. But the interrogator contains the laser, the optical and electronic components, and senses typically on infrastructure fibers these scenarios that I've shown down here. Pipeline monitoring, the downhole monitoring, I won't show today. This is not necessarily considered infrastructure fiber because it's a permanent and temporary purpose install that uses, in many cases, specialized fiber and is deployed in a certain way to maximize the sensitivity and the use for those applications. But all the others, like here, the border security or transports or power cables in the clean tech area, site security, these are all infrastructure fibers that are more or less standard fibers that are used by telecom companies. So the DAS sensing that we use relies on coherent Rayleigh backscattering effects. And that means that we are relying on the light being sent down a fiber, and the structure of the fiber itself, the glass, back reflects and scatters a very tiny amount of the light that is getting detected in the interrogator, demodulated and recorded onto disk. And on the right-hand side, you see a typical schematic view of the fiber on the right, and the light pulses going down along the fiber. And if there is no source, then that backscatter signal that you record for each single pulse would be unchanged. It would be stationary. Now, if I strain the fiber at some location, then that backscatter signal at this location only is changed. And you see that here, where we indicate the acoustic signals on some of the sensor channels. And the colors, the hot colors, indicate the strength of that strain signal that happens to be at that location in the fiber. The blue background is 0, so no detection and no sensing along those channels, just where a strain is, or a compression or elongation is imparted on the fiber through a strain field. That's where you see the seismic recording. That's where you see the seismic signal appearing. And so over time, you can see the second source coming on quietly and then getting stronger. You see some changes along the channels, depending on the source that is slightly activating different channels with different strength. So this is an example that you see in the following sets of slides as well, where we look in particular at the response on the infrastructure to certain impinging wavefronts. So the wavefronts could be earthquakes, they could be footsteps, could be anything that makes a change in the fiber itself. And I mentioned before that the distributed sensing locations and the point sensing locations do exhibit a slightly different property. So if you think about the fiber as a long straight line, we can precisely determine the distributed sensor locations at particular locations along the fiber by looking at the time of light it takes for a light pulse to reach a certain distance along the fiber. Now, with that, we can locate and pinpoint the sensor locations quite exactly. And if we have a wavefront impinging on the fiber, might be an earthquake wave, might be footsteps, cars, anything that radiates elastic energy into the ground where the fiber is located, the fiber will sense the change of the strain in its surroundings and will pick that up. But it will pick it up over a certain distance, not just at that sensor locations that are indicated here by those blue lines. It will use a certain gauge length. And the gauge length here would be from this end to this end. And it would record a phase shift, an optical phase shift of the light in the fiber between those two endpoint locations. And if the fiber is not moving at all, that phase change would be non-existent. It would be always constant. Now, if the fiber is compressed and elongated, within that gauge, you see an optical phase shift. And that is what we are measuring then. And it can be related directly to a strain measurement. So we are measuring the strain components of some elastic wave onto the fiber that is in line with the fiber, and the gauge length governs how we measure that. And that is the fundamental difference to point sensors. Point sensors measure that wave field as it goes through that point at a single location. So I've put here an example of a 3-component geophone that is cabled, that is digital and connected to a recording system. You have other systems like a nodal system that can be deployed on land or subsea that has a recording system built in, but essentially it is a point sensor that measures at a single point the particle velocity or the acceleration. And so we are measuring those direction vectors in 3D. So we can pinpoint very easily where the wave is coming from, what their strength is, and we can use it in further processing. But again, you only have that at very sparse location. I mean, depending on those systems, they can be quite expensive. And if you look at earthquake type broadband seismometers, they are more scientific instruments than industrial use instruments. So we're at a very high price point. And so you're ending up with hundreds of sensors, potentially in a survey or connected together, while for the fiber application, you are talking about tens of thousands of sensors being available. But a key point between the distributed sensors and the point sensors is that the reception characteristic is different between the DAS fiber sensors and the traditional point sensors. However, the measurements can be converted from one to the other. So as long as you record fully the wave field on the fiber, it can be converted into a point measurement. And you have here an example where we have a fiber recording of a seismic source that is a certain distance away, and you can see a first arrival here, a shear wave arrival here, some coda waves, and you have a certain amplitude characteristic that comes primarily from the introduction of a gauge length, where you didn't have one for the point sensor, but also some other effects caused by the source itself. So, but the key point is that we have many more sensors available, typically on a fiber, than we have on individual point sensors. And you might ask, what is the sensitivity of such a fiber sensor in comparison to the point sensors, those traditional sensors? And that varies. There are some factors impacting the sensitivity of the fiber. One is the fiber type itself. That means the optical properties of the fiber core material. You can engineer some of that to make it more susceptible to respond to certain effects, to stress and strain, or to chemical type recordings. Then you have the cable type, where you're looking at fiber arrangements and the geometry or the packaging. So the fiber, the optical fibers in here are those tiny little strands. The packaging are these bundling of fibers and filling material that you see. Also surrounding that is, in this case, a steel tube that protects it from other elements, and then yet another plastic sheeting. So it might be a very complicated system that transmits the strain onto the actual fiber sensors itself. And then the third component is the interrogator type. And the interrogator has the optical components, the electronic hardware in there, and that can be switched out and improved quite dramatically, depending on how you implement certain things in optics, in the electronics, in the interrogation and demodulation mechanism. So all of those can give you a chance to increase the sensitivity for either of those three. But you have to look at the system performance itself, which is a combination of all three of them. And in the best case, it gives you a higher signal-to-noise ratio, gives you a wider sensor pattern, many more sensors. You have farther monitoring distances, and potentially you have access to strain components and additional effects. So the answer to how sensitive is a DAS system as in comparison to point sensors is a multifaceted answer. It's not a simple answer because it depends on all those components. But when you look at infrastructure sensing, and you have no choice but to use the existing fiber in the ground, then your interrogator will be the driving component. So as sensitive as you can make it, the better it will be. If you have a chance to plug in some fiber cables of your choice, then you can tailor it to your needs, and you can drive up the sensitivity quite significantly. But let's look at some of the cable deployments and coupling along infrastructure. Here are a few scenarios where you might see or not see a fiber cable in here. Let's look at the train situation here, where you have the tracks. You have a fiber cable actually trenched in underneath this parallel access road. And in that case, the coupling of the fiber would be quite nice because it has direct soil coupling. But on the lower picture here, you see the same cable in a wayside trough that comes out of the ground, goes over a bridge, and then disappears again, potentially in the ground. So not an ideal scenario, but still can pick up quite nicely the strain. On the right-hand side, you see some of the extreme cases where you have power cables hanging from those pylons. And in those power cables, you have fiber optic cables for, again, telecommunication purposes, for controlling some of those power transformation stations and so on. But you can use them also for distributed acoustic sensing. In that case, you would be very susceptible to the swinging of the cable, to the wind, to the weather, but also pick up tremors from the pylons and transmissions of earthquake waves into those. And on the other end of the spectrum, you might have seafloor trenched cables, like here offshore UK, that go out to certain facilities out on the ocean and have power cables leading back onshore where those facilities are controlled. In all those scenarios, you can end up with a variety of telecom cables that are potentially heavily armored, like in here, or more typical, just standard telecom cables like the other two. But the main point is that infrastructure cables are all around us. And here's a Southern California map that shows the backbone of telecom cables in the vicinity of Los Angeles. So it's already quite dense here, and this is just a backbone map, not the individual fiber to the houses. So if you could imagine to use these cables for sensing purposes, it would be quite interesting. Now, what do you measure with those cables? Here is a earthquake recording on a telecom cable that was buried next to a pipeline. And what you can see here is a P wave arrival, a shear wave arrival. The green color is the low background noise, but then at some point you see the pickup of those earthquake waves appearing as those darker colors, and then the strong shear wave. But you have local noise sources here that are constantly active on the fiber. You also have local coupling effects that change the pickup of the signals. And that's something we'll have to look into a little bit further, because that goes directly into the fiber soil rock coupling and gives you an idea what the near surface material looks like and what the local subsurface material is for. So here is a little display of that same data, and you can see every sensor channel is about 10 meters apart, and you see that there are patches of characteristic differences between them. So on a distance of 150 meters, you have 3 different types of soil behavior, but in each of them you can see very nicely the peer arrival, the shear arrival, but we have to be aware of that the soil coupling impacts the signal strength and the character. And some basic questions that are being actively investigated right now is, can DAS on infrastructure telecom cables provide high quality data for things like earthquake analysis or ambient noise analysis, geotechnical analysis, or soil behavior? Currently, these questions are answered by standard seismic sensors that are used for these analyses, but can be augmented with DAS sensors, or can we do it even more efficiently with DAS sensors on infrastructure fiber? So that brings us to one of the uses in earthquake alert systems. So if you imagine that you have an earthquake going off at some location, and you would like to see what is the most likely ground shaking that will be occurring due to that, then you need a lot of seismic stations distributed in the vicinity of that. You need to rapidly detect the earthquake, then use the first P wave arrival to estimate the location and the magnitude, and then estimate the expected ground shaking here, the yellowish greenish colors, and immediately issue a warning before the significant ground shaking actually occurs due to the later S wave arrivals. So the warning times can range from seconds to minutes, depending on how far away from the earthquake you might be. And the data collected then is typically sent out, aggregated, and then sent out as alerts by scientific institutions or governmental agencies like USGS. And what can these alerts be used for? Well, simply on a personal level, get safe, cover under your desk. But in a more broad sense, you can slow or stop the trains, you can clear some traffic, you can move away from dangerous situations, or shut down entire industrial systems. And it allows you to go to backup power, and in the case of California, for example, isolating some power utilities to reduce fire initiation. This reduces damage, casualties, and avoids cascading failures in the aftermath of the shaking. Now, it's interesting to note that nationwide alert systems are actually only in place in Japan, Taiwan, Mexico, and Turkey. In other countries, you have a patchwork of small regional networks that can issue alerts, but it's not escalated up onto a nationwide level. And those systems that are currently in use for the nationwide level use standard seismic network station. In Japan, you can see there are hundreds onshore. There are some core stations offshore, since it's a high likelihood of earthquakes occurring there that have potential damage. So, but what if we could use infrastructure fiber to sense these earthquakes and potentially use it in an earthquake early warning system? Here is a comparison of the earthquake faults in the Bay Area. San Francisco is here. There are many, many faults, major faults, smaller faults. And when something ruptures here in a big scale, there's a tremendous impact. On the left-hand side, you can see the infrastructure fiber just in the Bay Area alone. It's extensively used. And what if we could put interrogators out there and end up with billions of sensors? Well, that's something that Professor Biondi at Stanford started to ask a couple of years ago. And the same fiber here can perform DAS sensing as well as communicate alerts. So Professor Biondi set up, together with us, a fiber-optic seismic observatory on the Stanford campus. And you can see the campus map here. We are located in the Bay Area on the Stanford campus, and it's sort of a figure 8-shaped rectangular array of fiber sensors that follows the fibers around on roads or on walkways across buildings in the campus. You can see the fiber cable here as it is deployed in the manhole. You can look in the manhole itself and see that we are having those fibers located in conduits. So it's simply gravity that holds down the cable and couples that cable to the environment. And the array ended up to be about 2.5 kilometers, one length through, and have about 305 channels in a double loop configuration, so 600 channels total, recording continuously since 2016 at a typical sampling rate that is used for earthquake type recordings. This also has garnered international attention in that the Victoria and Albert Museum had a display to display those novel data in a new fashion. And I encourage you to go online and play with the data a little bit. But why the interest? The interest was because infrastructure telecom fibers are all around us. There are novel concepts to be explored. Stanford is about 2-3 miles from the actual San Andreas fault. So there's a constant background noise of earthquakes occurring, but it's also in an urban environment where you have a lot of background noise that you can use for a variety of purposes. And here is a typical Stanford DAS recording over a snapshot of about 5 minutes. On the right-hand side, you see the actual live recording. And at some points there, you see some activity on certain channels that is related to footsteps, machinery, cars, buses, and you can track that over time. On the left here, you see a typical recording that has a multitude of effects in it. Most importantly, there is an earthquake here, these whitish colors, and there is background noise. So the earthquake stands out very brightly from the background noise. You have those sloping features here that are traffic noise, buses, cars, bicycles. You have those stationary signals that are pumps. So depending on what you are looking for, you can isolate those signals and you can process it. We focused here on ambient noise analysis and earthquake analysis because these two are complementary to each other if you want to use it in the long term for some sort of ground motion prediction and earthquake early warning systems. The ambient noise is acoustic daylight noise, essentially uncontrolled and often unknown random sources of elastic and acoustic waves. So if you have sensors along a fiber and you have those popping sounds, elastic waves going off, all the sensors record that, but you can now turn a reference sensor into a virtual source by cross-correlation and summing all the contributions of those sources and summing it over time to build up a virtual active recording, as if you would have an explosion set off at this receiver location. And that's a quite powerful mechanism in that you can actually track that over time. In here, we stacked over a certain part of the data in September, October through April. And if you look into the box, you see features appearing that get stronger over time. That is roughly when the rain starts on campus. And that's when the soil has a much higher moisture content. You can analyze the data. You have P wave arrivals, shear wave arrivals, you have reflections and scattering. So that makes it very useful to come up with velocity curves and the changes to the velocity curves. And these velocity profiles can be obtained at each sensor locations, in this case at increments of 8 meters. So you have soil conditions that can be determined and tracked over time. But more importantly, you could use that to predict ground shaking and the risk to structures. So that is one use of this data. But you can also use it for sensing earthquakes. And typically at nighttime, it is quieter and a good opportunity to look in certain frequency ranges from 1/4 to 10 hertz for earthquakes. And we were lucky to, in the first days of the installation of the array, see some of that earthquake that was initiated in Oklahoma, travel across the US and being recorded in the Stanford DAS Array with a weak P wave, a very strong shear wave. There's some legal noise right before that, but you can clearly see that. So especially if you stack the signals, you see that it compares very favorably to a standard broadband seismic system. Here the shear wave arrivals line up, the P wave arrivals line up. The general noise level is different, but you capture essentially the same data. So let's look at an earthquake recording that happened the earthquake happened in Mexico in 2017. We actually recorded that on a pipeline in Mexico. It was a major earthquake that shook Mexico City strongly, and we clearly saw that on the pipeline. We also saw that on the Stanford DAS Array here as a strong shear wave arrival and the P wave arrival. And if you, again, stack those sensors all together, very nicely a P and S arrival emerges, and you see those seismic signals. Now, let's look at the pipeline itself. There is a standard seismic station about 100 kilometers from the pipeline, so we have a reference. But the sensor network, the sensor array along the pipeline consists of about 29,000 sensors that are hooked up in certain segments. In each of those segments here, you can see the arrival of the P wave, the shear wave, in a very complex coda for each one of them. The primary purpose of the sensing system on the pipeline is to detect leaks and control the compressors. But we can also use it for perimeter detection and other opportunistic recordings. In this case, recording the entire complex earthquake wave field on the entirety of the system. So that demonstrates clearly the use for an early warning application to augment some of the traditional seismic network stations. So it's quite powerful to be able to detect some of those effects. Now, I want to show you here one example that happened in the transport monitoring. The primary goal here was to monitor trains on dual tracks, also detect wheel flats, rail brakes, and other conditions of the train. But it turned out to be an opportunity to record an earthquake in the UK, in Wales, of a magnitude 4.7. And here's a timetable of the train, and you will see the recording mimics that. So you see a north traveling train here in the yellow color, in the blue color, a south traveling train. And here you see it in the actual recording. The trains here pass by each other at this point. This train makes more noise. It's probably a different type of train. This one goes at various speeds. It's a little bit less noisy. But you can see here there's an event that is nearly instantaneous across the array. And that is actually the earthquake happening at this exact time being sensed. When we zoom into that, we see earthquake waves, P wave arrivals, 2 of them, and shear wave arrivals, 2 of them. So you can go in very fine detail and get a sense of what the earthquake recording impact is on your train tracks here and the local scattering of the near surface. So the earthquake was about 170 kilometers from the train tracks, and we still could sense that very nicely on this infrastructure fiber. California Institute of Technology also put out a DAS array in Pasadena, where they hooked up to infrastructure telecom fiber throughout the city. And on the right-hand side, you can see the recordings on a Friday afternoon. And everybody wants to go home from work. So you see all those traffic patterns here, starting and stopping of trains and starting and stopping of cars along highways and city roads, people walking, and so on. So this is on a length of about 10 kilometers. So the urban environment is very noisy, but you can get a lot of information from it, but less on the earthquake side. However, we did manage to record an earthquake, and this is the La Habra earthquake, which happened about 30 kilometers from Pasadena. Pasadena is here, La Habra is here, and if you look at a little square, that's actually our office in Brea. So we definitely felt it. We didn't have any damage, but it picked it up very nicely on the urban array in Pasadena. In some areas, the coupling is better. So you have the direct arrivals, but also you see a lot of coda waves, which gives you a lot of information about the actual soil conditions underneath the fiber, which is important for risk mitigations and for predicting ground shake movement. So this is in a noisy environment, in an urban environment. But what if you take that entire array out into the desert? And so together with JPL and Caltech, we put it out in the deep space communication network in Goldstone, which is in the Mojave Desert. There is nothing around except some radio dishes, maybe occasional wildlife, but it's heavily restricted access. And the fiber connects individual radio telescopes on a length of 50 kilometers. So it's a very quiet environment. And we can see regional earthquakes, small earthquakes, which are about 30 to 100 kilometers away, very nicely high frequency P wave arrivals and codas, shear wave arrivals and codas, and scattering from the near surface. So a lot of information is in the data. But then on the other end, we also see very far away earthquakes. This is an 8.2, a very strong earthquake in Fiji in the South Pacific. So it has to travel around the globe to actually reach us here in Southern California. And the difference between the left picture and the right picture is that you have very low frequency and you're measuring travel times in the order of minutes, tens of minutes, while here you are measuring travel times in the order of tens of seconds. But in essence, you're sensing the same kind of information, just at a lower frequency, and you can pick it up from around the globe. An additional advantage here is that we have a reference station that is embedded in the Southern California seismic network as a reference, so we can calibrate the recordings here against those large or regional earthquakes. So all those extremely quiet environments give us an observation with a high signal to noise ratio. So if you can put infrastructure in quiet environments to use, that's where you get excellent data. So we can record useful information. We have established that. And that means that with DAS systems on infrastructure fibers, we potentially might detect earthquakes quicker, closer to the epicenter. And we can obtain earthquake info like as magnitude and location, which are the primary ingredients for early warning systems. We can also estimate the soil parameters and subsurface properties with high resolution. And through that, we find some of the ground shaking predictions that are currently used in alert systems. And just to show you here the US backbone fiber map, it's pervasive throughout the country, and especially in regions where we are interested in having alert systems in place, which are, for example, the Pacific Northwest, the Cascadia area, which includes Vancouver, Seattle, Portland, those areas that are high-tech industries and highly fibered, and also have offshore fibers available. These are candidates for earthquake early warning systems on infrastructure fiber. Bay Area, of course, where the Stanford system is located, and Southern California, of course, where the Caltech system has recorded the data. So you can think of tying them all together into a West Coast regional network that triggers on alerts locally and communicates back and forth between all those. Or you can extend it to the entire US very easily. But these are the high impact areas with existing dense fiber installations. So what are the opportunities really for us here? The opportunities are that the fiber infrastructure is really all around us and can be used for DAS sensing and makes very large sensor arrays possible, which were previously just impossible cost-wise or effort-wise. Very fine spacing, and we can set up systems that are either embedded or ad hoc. They might be completely running 24/7, or they might switch on as a byproduct of an earthquake and record in the aftermath. So you don't have to put out sensing stations, you just have to take out interrogators, connect and switch on, and you're ready to measure aftershocks right after the earthquake hit. The networked sensing system can really turn data into information and provide situational awareness. So if you think ahead of that, artificial intelligence would fit in there, machine learning would fit right in there. And with the vast amount of data that you get from these kinds of systems, it's tantamount to look at analysis algorithms that are sufficiently good in computational speed and storage. And these are the key ingredients to really unlocking the potential. Currently, we have been using traditional DAS systems on some infrastructure monitoring applications, security applications, transport, and oil and gas. But I think some potential future uses are clearly on the horizon with early warning systems for earthquakes, tsunamis, but also smart infrastructure in general and high-resolution geotechnical applications. And I just want to end here with some of the potential scenarios that I picked off from some of the applications. Japan, for example, has a very dense network, but it is single point sensors. Imagine if you could use the entire fiber system on land, or the entire fiber system that already connects all the nodes offshore to actually get a much better coverage of an earthquake that again might hit the west coast of Japan like it did in 2011. You would have at least a 10-15 minute warning time to safely shut down everything and not end up with a large disaster zone. So you can translate that into various sets of scenarios in different countries, different applications, but that's where I see it going in the near and midterm. On the other hand, if you look at smart cities, smart buildings, and smart infrastructures, some of the cities in the US clearly have caught on to that and have put already a fiber optic master plan into place where they think ahead tens of years and decades in advance and put it into their growth plan, building plan, and have that available for a variety of purposes. And of course, hooking up a DAS interrogator to something like this also can give you a lot of information about the geotechnical subsurface information, for risk mitigation, for earthquake scenarios, and so on. So I think the future is bright there. And at this point, I'd like to stop and take questions from the audience. And I leave this picture up here. And this picture here is actually a link to the big glass mic display. It gives you an opportunity to actually interactively play with some of the snippets of the data that we collected at Stanford. I hope you have fun with that. With that, thank you very much.
Thank you very much, Martin, for a very informative presentation. I think I maybe have a very basic question, and this is obviously understanding the difference between fiber optic sensing and point sensors. So the infrastructure cable is usually buried underground. So how is it that you can tell sort of where specific events are taking place?
Yes, that's a very good question. We know very well where on the fiber, actually in the glass, where on the glass the actual disturbance occurs. And we can measure that precisely down to the nanosecond and down to the meter, centimeter level. But you have to translate that into a true location on the ground in XYZ, so in east, west, and depth. And for that, you have to apply some tap tests, which means you go to locations where you have access to the fiber. That might be in manholes, that might be in network switches, that might be in any location that you roughly know where the fiber is buried, and you tap there, or you use a small hammer on the ground and tap the ground if the fiber cable is actually buried 2-3 meters down. It will pick up that small amount of energy, and you then can look back on where you see that in the recording, on which channel. And you can do that for a sparse set of locations. For example, where those, in this picture, where those fibers turn. So you would end up with 8 points, and you could interpolate in between. Or if you have enough graduate students, you could actually walk and let them hit the hammer every meter roughly along the fiber, and you will see that for each of those little activations. And you can end up with a very detailed fiber map in that case. So these are the tap tests that are commonly performed to calibrate the fiber locations.
Thank you. I should probably explain, to ask a question, you can type it in on the box to the right there. But let me ask you, you mentioned the potential for tsunami warning systems. Now, I assume there's a trade-off. Maybe I'm assuming the wrong thing. Obviously, you need to have an interrogator at a particular distance. How does that work in an ocean environment?
Yes, that's a very good point. Well, the simplest is if you have an access to the fiber on land, you can try to interrogate from there. But it will reach only a certain distance, maybe 40 kilometers, maybe 80 kilometers. And then you have the opportunity to potentially put those interrogator boxes in special compartments onto the sea floor. And that is actually done for the standard tsunami systems, like in Japan or Taiwan, where they put the standard seismic broadband sensors into pressure vessels and permanently placed them on the seafloor and connected them with power, with a fiber, data transmission, and so on. So that infrastructure is already in place for the standard systems. And it would just be a matter of repackaging that interrogator box into that kind of vessel. And OptaSense has done in the past that kind of design and makes that deployment possible. So you can then think of spacing the interrogators out on the ocean floor at intervals where you need them, and connect them all together in the network cable, control them, sense them, bring the data back. So it's possible.
Good. You mentioned that some cities and communities are incorporating seismic sensing plans in their city planning. Are state governments moving forward on this as well? And I guess specifically, how about California and the specific Northwest states?
Yes, some of those cities are having a fiber plan in place in general. I think they are slowly becoming aware of the DAS sensing opportunities based on the work that Stanford has been doing and Caltech has been doing. And so that is slowly bubbling up on the importance level on their end. On the state level, certainly regulators are aware of that and discussions are going on. I think behind the scenes, there's a lot of discussions on what could be done with it and how could be put in place. And especially in California, since California could benefit quite a bit of early warning systems with the large fault zone in place for major earthquakes, that's certainly something that some of the earthquake alert systems that are being prototyped are looking at. So I'm sure that at some point there will be some tests being done, and hopefully the future is bright to make actually use of those dark fibers that are just lying around now and could be put into really productive use on that end.
Well, we certainly hope that some of those state governments, if they're not listening now, will be listening to us on the YouTube channel. I have a more technical question from one respondent. What is the exact sensitivity of the minimum strain that DAS can measure?
If you're just looking at the fiber itself, you're going down to picostrain levels, so fairly small levels. But when you look at how the actual fiber cable is coupled, then you might lose a little bit of sensitivity, or you might actually transfer that kind of small changes directly onto the recordings. So I know I cannot give a definite question, but it really depends on how the fiber is coupled to the subsurface and how that transmission of the strain on the fiber is achieved. And if it's coupled very well, then it's competitive to conventional geophone systems or accelerometer systems. Certainly in the type of downhole applications that we have in oil and gas, it reaches that level because the coupling is usually very, very good. It's cemented in and couples directly to the rock. So some of the infrastructure fiber is actually in a similar situation, and some of them is just loosely coupled. So there's a wide variety of sensitivities out there.
That's helpful. We're coming up to the hour, so I guess we'll have kind of one last question. And I wondered if you could kind of elaborate a little bit on sort of what kind of warning times we're talking about. You've talked about some of the advantages, but how much warning do earthquakes need, and how does that all work?
Yes, I think those warning times can be quite variable. They can range from a few seconds to tens of minutes. And it all depends on how far the impacted area is away from the earthquake itself. So normally, a few seconds are enough to trigger certain alerts, like shutting down critical infrastructure, powering up backup supplies, putting hospitals on alert, and going into certain emergency modes. That's possible within seconds. And if you think, for example, of largely populated areas like Southern California, Northern California, and the Pacific Northwest in particular, where you have the Amazons, in Seattle, for example, that might be impacted quite heavily from a large earthquake in the Cascadia subduction zone, they might have 10, 15 minutes, 10 minutes warning if it happens on the southern edge of the Cascadia subduction zone. You might have a few to 10, 15 seconds warning if it happens in the northerly section. But clearly, it would be enough for them to switch their facilities into an emergency mode and power mode, and potentially also stop some of the subways, the trains, the buses, airports, and the critical infrastructure that is really impacted potentially by that. So again, the answer is there's a wide range of warning times, but a few seconds are potentially enough to give you enough time to react to it. And depending on the alert system, it can be achieved. But again, it relies on having sensors very close to where the earthquake occurs. And with some of the standard systems, they are quite sparse. Those broadband stations are scattered throughout. And potentially, with some of the infrastructure fibers, you end up close to the earthquake itself. And that gives you the precious few seconds that you might gain between the arrival of the weak P wave and then the strong shear wave shaking that really brings the destruction with it.
Well, thank you very much. We do have some more questions, but I have to say we're sort of at the top of the hour, so I would encourage people. On the last slide, we've got your email address, and I'm sure you're prepared to answer some of the more, actually more technical, more specific questions that some people do have. I will also add that this webinar will be posted on FOSA's YouTube page probably in the next 24 hours or so folks can go back over. Also a reminder that exactly 4 weeks from today, we will be having another webinar, this time with FIOPS and some oil and gas applications. So we'll have more information about that posted on our website shortly. But thank you, Martin, for an extremely informative presentation.
Well, thank you very much.
That concludes. Yep, and that concludes the webinar.